But no, let's go ahead and nail down the schedule. So we have our last lesson this week. This is it. There's our last lesson. We'll have an assignment to go with it. Then we'll be done with all of the Algebra 3. Next week, we'll meet on Tuesday. I don't know exactly what we're going to do. We may look at the final or something. Haven't 100% nailed down what we're doing next Tuesday yet. But we'll have that. And then we have our final next week. Now, the final for this class, this is 0B. So you are actually on Friday. Our final is Friday morning at 7:15 in this class. You come to class right here and we'll have the final. Now, the good thing is you can exempt the final, right? You may not have to take it. If you haven't had more than 4 absences in advisory or in here, no more than 4 tardies in here, you have no missing assignments. Let me look right there. I see a few missing assignments. There's not a whole lot of missing assignments. There's a few. Some of you have a few missing assignments, or one missing assignment. If you have no missing assignments and your grade is 75% or greater, then you can exempt absences, all that other stuff. So then you don't care when the final is. But here's the nice thing is if you're exempt and say you've got a 78.6 in this class, and you're like, oh man, if I had a 79.6, it'd round up and be a B. Well, if you are exempt, you can choose to take the final and try to raise your grade. Now, if you bomb the final, you make a 40, I throw it out and pretend you never took it. Oh no, they didn't take the final at all. No, it's gone. So being exempt is wonderful because it gives you options. Now, if you're not exempt, you have to take the final. If you bomb it with a 40, you're ready to go down. But you're not going to do that. You're going to do well if you take the final. So the final is next Friday, 7:15 in this class. You just log in and we will have the final during class. So that's what we are looking at for next week. Get that schedule all lined out. And then again, we have that Tuesday after. That is our last day of school. Let's see. All right, let's put up this week's buzz up here to see what we got. Okay, looking at our grade screen as usual. Scroll all the way down. We have graphs of rational functions. And then the semester finals right there. Graphs of rational functions. That's what's due this Sunday. I will be sending an email out this week to give you the deadline to get everything turned in, by the way. If you're missing anything, if you have anything here that shows you've not submitted it, that's the submitted date column right there. Shows when you turned it in. And of course, you should have a grade for it right here. Some of this with the matrix assignments, you might have done it in Khan Academy and forgot to turn it in, but I tried to go look at Khan Academy to see if you were logged in, it kept your grade, and I went ahead and transferred your grade. So you may have a grade without a submitted date, which is fine. As long as there's a grade there, you're in good shape. But yeah, we'll have all of that. But I'll send an email out on when you have to have everything in to be exempt, because I have to have a cutoff date for that so I can send out the email saying you're good. All right, let's go to that graphs of rational functions right here. Graphs of rational functions lesson. So this requires we talk a little bit about rational functions that we've haven't gotten very deep into since it's the end of the year. But we're gonna hit it today. We're gonna hit some of that. So a rational function, again, is when you have p of x over q of x. Like it's 3x squared minus 5 over 2x squared. You know, you got a polynomial over a polynomial. And it says with no common factors and q of x cannot be 0, right? The denominator cannot be 0. So let's talk about the graph of a rational function. And we've looked a little bit at the graph last week. But the y-intercept, if there is one, is the value of f of 0. If you substitute 0 in there, give you the y-intercept. The x-intercepts, if there are any, are the zeros of the numerator. So you solve whatever is on top, and that will give you the zeros of the numerator. The vertical asymptotes, remember, are the zeros of the denominator, the solutions of whatever q of x is when it is set equal to 0. The horizontal asymptote is the value that f of x approaches as x increases or decreases, which we see on the graph. And we also know it's based on the degree of the numerator and the degree of the denominator. So determining the behavior of the graph between and to the left and right of each x-intercept and vertical asymptote is crucial for describing the complete graph of a rational function. For example, with the graph 5 over x plus 1, 5 over x plus 1. Well, let's just play with that for just a second. I'm going to put that on paper. If we're talking about the graph of f of x equal 5 over x plus 1. 5 over x plus 1. My 5 looks a little rough this morning. Okay, so when we talk about it, we know there's a vertical asymptote where the denominator equals 0. So x plus 1 equals 0. Solve that for x. At x equals negative 1, there is a vertical asymptote. We'll abbreviate it like that. Vertical asymptote at x equals negative 1. We know that there's a 0. Where's there 0? Well, where the numerator equals 0. So this at 5 equals 0. 5 doesn't equal 0. Let's look at the horizontal asymptote. The degree of the denominator is higher than the degree of the numerator. This is x to the 0 power. This is x to the first power. Because there's not an x up here, so it's x to the 0 power. So since this is larger, there's an asymptote at y equals 0, which may explain why there's no 0. It's not going to touch the x-axis. See, what else were they looking at on here? The y-intercept. The y-intercept is at 0, 5. It says because this equals 5. Y-intercept. See, y-intercept 0, 5. There is no x-intercept, vertical asymptote, and horizontal asymptote. Now let's actually just put that in Desmos and see what it actually looks like. Equals 5 divided by x plus 1. Well, there it is. See, it does not have a 0. It does not touch the x-axis because there's an asymptote, a horizontal asymptote at y equals 0. So since the top was just a 5, we do not have a 0 in this. But we do have, we said at x equals negative 1 is that horizontal asymptote, the vertical asymptote. So we see as he comes in from the left, it goes down to negative infinity, never making it to the 1, the negative 1. And then coming from the right, it goes up to infinity as it approaches that asymptote. So we see the vertical asymptote at x equals negative 1, the horizontal asymptote at y equals 0. The y-intercept, we said, was at 0, 5. There's the y-intercept. And no 0 for this one. And we can see that just looking at the equation. So review the above concepts to explain each of the above conclusions. Test your skills. Determine the y-intercept, x-intercept, vertical asymptote, and horizontal asymptote of the following. Now, this is almost the exact same equation, except it's x minus 1 instead of x plus 1. So everything will be the same except for the vertical asymptote. The vertical asymptote will move to be at x equals 1. See if we just change that to a negative. See, it just changes the asymptote to be on positive 1. But everything else will be the same. Let's look at one that's a little trickier. Let's do D. Let's do that fun right there. I'm going to copy that to the paper here. Okay, so for this one, the 0 is going to be where the numerator is equal to 0. So this is where our 0 is. It will cross the x-axis at -2. The vertical asymptotes are where this is equal to 0. Remember, when we have a quadratic equation set equal to 0, we factor it if possible. This one does factor x plus 1 times x plus 3, right? Because 1 times 3 is 3, and 1 plus 3 will give us the 4x right there in the middle. Got my pencil here. So the asymptotes were x plus 1 equals 0 and x plus 3 equals 0. So -1, -3. We have asymptotes where x equals -1 and x equals -3. Those are the vertical asymptotes. So we have a 0 there, vertical asymptote. Let's look at the horizontal asymptote. This is first degree. The denominator is second degree. So that means the horizontal asymptote is at y equals 0 because the denominator is larger than the numerator. And let's see, it says how did it tell us to find that? The y-intercept is the value of f of 0. So if we put f of 0 in there, 0 plus 2, 0 squared plus 4 times 0 plus 3. So it looks like it should be at 2/3. Because that's when f of 0, if we substitute 0 in for x, the y-intercept should be at 0, 2/3. Because when we substitute 0 in, that goes away, that goes away, that goes away. We just leave the 2/3. So let's graph this and see if we're right on all of those items. So the numerator is x plus 2. And the denominator is x squared plus 4x plus 3. All right. Well, I don't think we didn't get the y-intercept right. It looks like. Oh, wait. I got plus 31. Never mind. X. Oh, that's not squared. Why is that not squared? There we go. X squared plus 4x plus 3. This is the correct equation. Now, I've got it typed in correctly now. We said there are two vertical asymptotes. One is at -1 and one is at -3. Oh, and we see those. That's it. You see, we have two vertical asymptotes. We said that the 0 is at x equals -2. There it is. We do see a 0 there at x equals -2. And we said the y-intercept is going to be at 2/3. 0, 2/3. It is 0.666667. So graphing it, we can see that everything that we did on paper is exactly what it looks like. And there's that horizontal asymptote at y equals 0. So as it goes left, it's approaching the 0. As it goes right, it's approaching the 0. There is a horizontal asymptote there, even though there's also a 0 at -2, 0. So, but that is nailing it for this one right here. So if you look at these other ones, x minus 1, x plus 1, that one's kind of interesting. We have a first degree on the numerator and a first degree on the denominator. So the coefficients are 1. That's going to have the horizontal asymptote at y equals 1. And then a vertical asymptote at -1. It's going to have a 0 at 1. And then the y-intercept to be at -1. All right, let's talk about slant asymptotes a little bit. And holes. I want to talk about holes as well. Although our assignment, you're not going to have to do slant asymptotes, and I don't believe it talks about holes either. So when the numerator has a degree exactly one more than the denominator, the graph of a function has a slant asymptote. And the way you find out what the slant asymptote is you divide. You actually divide the numerator by the denominator to find the slant asymptote. If you remember, go back to synthetic division or long division. We've done some of that. We can do it. But I want to graph this and take a look at that real quick. See what a slant asymptote is going to look like. And we might play with it real quick just to actually calculate it. X squared minus 4x plus 3. Oh, it's almost the denominator. So I'm going to copy that, place the numerator, minus 4x plus 3. And x plus 2 is the denominator. Okay. Oh, we see there is that slant asymptote. See how that looks like? It does have an asymptote, but it's at an angle. And it says we can calculate that. Let me write this down. X squared minus 4x plus 3 divided by x plus 2. It says we can calculate that using division. Well, if you remember synthetic division, we do -2 is what we use to divide. Since this is x plus 2, we use the opposite. And we divide that into the coefficients. 1, -4, and 3. We bring the 1 down. -2 times 1 is -2. Add those together, it's -6. -2 times -6 is 12. Add those together, so it's x plus 6 plus 15x plus 2. So we've got a kind of an odd, we got a remainder, 15x plus 2s. But so x plus 6 plus 15x plus 2. So let's type that in and see what that looks like. Y equals x plus 6 plus 15 divided by x plus 2. Oh, I messed something up there, I think. It gave me a really odd graph. If I just did x plus 6, what does that do? That's not it either. Oh, this little. Oh, x minus 6. Oh, yeah, it is an x minus 6. If I look at my paper, this was a minus. And I wrote x plus 6. Pay attention to the negatives, Mr. Brock. Pay attention to this. So x minus 6, and there's a remainder. But if we put that x minus 6 in the graph, oh, there's that slant asymptote. And it gets closer and closer and closer at both ends. The graph goes both directions. That x plus 6, just using long division, is how we calculate to get x minus 6. Interesting. I do want to talk about holes. Holes are interesting too. With a graph with a hole, if we have, and I'm going to put this in factored form, right? So if we have x minus 2 times x plus 3 over x plus 1 times x minus 2. All right. I wrote it in factored form. I could have put them in x squares or whatever. If we look at this, this can be simplified because we have an x minus 2 being divided by an x minus 2. So this actually simplifies to x plus 3 over x plus 1 because these will cancel out. So the graph will look like this. We'll have x equals -1 as a vertical asymptote. We'll have x -3 as a 0. We'll have a y equals 1 since they are the same degree as a horizontal asymptote. But what happens with this x minus 2? Here, I'm going to graph this because I want to look at this real quick. Okay, so if I put this, I can put this in factored form in Desmos. It's happy with that. x minus 2, x plus 3. Okay, there's the numerator. And then I've got x minus 2 on the bottom. Oh, minus. There we go, Mr. Brown. And x plus 1. All right. So here is what we're expecting. Let me zoom in here. We said that we would have a vertical asymptote at x equals -1, which we see that right there. Oh, I don't like that. It puts the same color. Let's change the color. Let's change it to blue. Okay. So there's that vertical asymptote right there. We said that -3 would be our 0, and we see right there it crosses -3. And, well, we have the y-intercept there. But what about this x minus 2 that canceled out? I don't see anything on the graph that makes me think there's anything weird going on there. Well, if x minus 2, something is going on when that equals 0. So at x equals 2, there's something going on with our graph because that is part of this that canceled out. This is actually a hole in our graph. Literally a hole in the graph, which means it doesn't exist there. If you graphed it, you'd have to take out x equals 2. And you're like, but there's not a hole here. Well, there is. You just have to zoom in a long ways to get there. Because let's look. Let's look at this graph. I'm at 4. I'm going down 3. Keep going. When I get down to 2, look at there. There is a hole in the graph at x equals 2. It's undefined right there. And if we were graphing it by hand, we would actually draw a hollow circle right there to indicate that this graph includes everything on the line except where the little hole is, where the little circle is. So there's literally, you can't see it unless you click on it in Desmos, but it is right there. 2 is undefined. So that's where you have to know, looking at the equation, we have to know there's a hole because the same factor, you factor everything in the factored form and it cancels out. If there's the same term on the numerator and the denominator, that creates a hole in our graph. And I don't know if I could zoom in enough to see it. I've done it before. You gotta get a long ways in there to ever. Where's the 2? Oh, the 2's right there. You gotta get a long ways in there to ever show up, but it will at some point show up if you keep zooming in. But every time you click on it, it's undefined. So I don't think I'm gonna try to zoom in. That's not easy to do. But yeah, holes. So anytime that you have the same term on the top and bottom. So for example, they did this one, x minus 1, x squared plus x minus 2. So if you factor x squared plus x plus minus 2, you get x minus 1 over x minus 1, x plus 2. In that case, you've got x minus 1 on the top and the bottom. So this would simplify to just be 1 over x plus 2. That's what that equation would simplify to. But at that x equals 1 would be the hole in the graph. There'd be a vertical asymptote at x equals -2 because of the denominator, but there's a hole at x equals 1. So the graph does not exist there. So, all right. And there's some more problems to just test to find the slant asymptotes. And you can check your answers. If you click there, there is a document there that I looked at. And this is just going into the more detail. So really, that is all that we're looking at this week. Is I wanted to bring up the holes and the slant asymptotes. But let's look at the assignment, because the assignment's basically finding this information here. So on this assignment, it's right here on the screen. I'm going to see if I can make this smaller where we can see more at a time. So you can copy this to a Google Doc. I think you can actually literally just, you can copy it. You can copy all this, or you can take a picture of it, or you can print it out if you have a printer. But you have 2 problems right here, 2 problems. And this is where you turn it in at. Turn in your Google Doc or turn in your picture if you want to do it on paper or whatever you're doing. But here's what it wants you to do. Graph this. 4 over x squared minus 2x minus 3. And yes, you can use Desmos. And if you want to use Desmos and just take a picture of the graph from Desmos, screenshot it and put it on your Google Doc, you can do that. Or you can look at Desmos. If you got this printed out, you can draw this by hand on this graph, however you want to do that. Give the domain and range. Right there. Give the x and y intercepts. List horizontal asymptotes. List vertical asymptotes. Same thing down here. Domain and range, x and y intercepts, horizontal asymptotes, vertical asymptotes. Let's talk about domain and range real quick. Let's look at this graph that we have right here. What is the domain and what is the range? The domain is all the possible x's, which in this graph, that would be negative infinity to infinity, except x cannot be -1, right? Because there's an asymptote at -1. This graph will never equal -1 for the x. Likewise, the domain goes up and down from negative infinity to infinity, except for y equals 1. There's a horizontal asymptote at y equals 1. So it would include all real numbers except y equals 1. All real numbers in the domain except x equals -1. So that's what it's looking for there, domain and range. X and y intercepts you can get. And, when you graph it, you can see that too. There's the y-intercept. There's the x-intercept. But you may be able to look at this equation and get it. These will not have holes. Doesn't ask you for any holes. Doesn't ask you for any slant asymptotes. Just domain and range, x and y intercept, horizontal asymptote, vertical asymptote. And just turn that in down here with your Google Doc, whatever. But there is all what you need. 2 problems. And that will wrap up our year for Algebra 3. So missing things, get those turned in. I'll be sending out exemption emails. I don't know if it's going to be Monday or Tuesday because they have to send me the attendance report. The office will compile all the attendance reports and let me know how many absences you've had in my class. Let me know how many absences you've had in 6th period advisory, because you can't have more than 4 there either. And I will get that, I'm sure, by Monday or Tuesday. So I will be sending out emails next week. I'm hoping to do them on Monday. I really am. I don't like to wait until Tuesday. But that being said, that would be the deadline for exemptions. Like, probably, I'm guessing it's going to be Monday morning at 7 a.m. If you want to be exempt, have everything turned in by Monday morning at 7 a.m. But I would still accept late work until like Thursday morning. I mean, maybe Thursday noon, just for credit. You couldn't be exempt if you turned it in Wednesday or Thursday, but you could still get credit for it and raise your grade. So I like to give you that opportunity even after exemptions time. But I'll get those emails out on deadlines as soon as I get more information on when I'm going to get the attendance report. So sometime I'll get that out before the weekends. I'll get an email out telling you the deadline. But just get everything turned in today. Then you don't have to worry about it. Now, nobody's missing like 10 assignments or nothing. It's not that drastic. So some people are missing more than 1 or 2, but nobody's missing like 10 or 15 assignments. So get it done, get it turned in. I'm going to make sure and get everything out to you that I can get. If you got questions on anything, this is an A-Day Friday. So we just have class on Thursday. If you need help with anything, or if your grade's below 70%, I'll see you Thursday. Otherwise, we're done, guys. I'm not going to keep you another hour or anything. You can get this done. Get ready for summer. We'll see ya.